All right, so we are in Algebra 1. We are starting our brand new unit, Unit 8. Today's date is Tuesday, February 4th, 2020. And just as a heads up, this is what our guide looks like. We have 9 lessons, 3 quizzes, and then a test. And then tonight we have 2 homework assignments. All right, so what is our objective? Jade.
Determine if tables, graphs, and real-world problems are either exponential growth or linear growth.
Precisely. So I'm going to show you a few different things in terms of the tables, in terms of the graphs, in terms of what real-world problems, words you're looking for, and then a bunch of examples. So we've talked about linear growth before, and it's what happens when I have a constant amount in the x and the y. So if I am going from 5 to 8, I'm adding 3. If I'm going from 8 to 11, I'm adding 3. If I'm going from 11 to 14, I'm adding 3. So the main thing, I shouldn't say the main thing that you need to check, but one of the things that I could offer you as a trick question is I'll change your x's to weird numbers. As long as you're increasing by the same amount for your x's, you can ignore the x's. You can only pay attention to the y's. So because these are going up by a constant amount, I can kind of ignore the x's now. Same thing for the x's on the next table. I'm going up by 2, so plus 2. I'm going up by 2, plus 2. I'm going up by 2, so plus 2. And then once you figure out, hey, I'm going up by a constant amount, go ahead and ignore the x's. We really only want to pay attention to the y values. All right, so now that we know that the x values are going up by a constant amount in both of these, and again, it will be a little bit maybe confusing later when we compare these two, but I'll repeat the information. The y values, I need someone to analyze what's going on for the first table. Wyatt?
Multiplying by 2.
Multiplying by 2 every single time. So from 2 to 4, I times 2. From 4 to 8, I times 2. And from 8 to 16, I times by 2. What about the y values in the second table with the quiet raised hand? What is the pattern? Eamon?
It is plus 4, and then it's plus 4 plus 4 plus 4.
Adding 4 each time. Perfect. And that's the main difference. If I'm ignoring the x's because they're going up by constant amounts, if one is multiplying by a constant number, and that number is called your ratio, because it could be a fraction. So I could be multiplying by 2/3 and 2/3 and 2/3. Sometimes I'll call this the common ratio. So that's another term for it. The word that I'm going to use over here to describe this 4 is called the difference, because the difference between 8 and 12 is 4. So this is going to be called a difference. And again, sometimes I will call it the common difference, because I don't actually know why we call it the common ratio. I guess it's all of them are the same, so they're common. I don't know. But yeah, those are the vocab words. So the main thing to take away from these two tables is when I multiply every single time, that is exponential growth. And well, it's not. It might be decay, but for all of today's lesson, I'm only going to be doing exponential growth, so I'm always going to be multiplying by a number that's greater than 1. If I multiply by a half and multiply by half, that's still exponential, but it's now exponential decay. We'll talk about that another day. And that did rhyme. All right, so this one is linear. It's linear. I can't spell linear because I'm adding the same amount every time I have a common difference, not a common ratio. And to be very clear about what I'm saying, the common ratio for the first table is 2. The common difference for the second table is 4.
So you're just talking about the bottom.
Yeah, I'm ignoring the x's now that we know the x's are going up by a constant amount. I'm only talking about the y's. And I have to be careful about using the word bottom because sometimes the table will be side by side instead of up and to the top and the bottom. Yeah, good insight. But next time, if you could raise your hand, that would be better. Thank you. All right, so, and this is in words what we basically just set up here. So if I'm talking about a linear relationship, this table on the right-hand side, the y values have equal, and what's that green word that we just wrote down? Who has it? Kira?
Difference.
Yeah, they-
Ratio.
It's one or the other. Linear means difference, yeah. Equal differences. And finally, in exponential relationships, the y values have equal, Larissa? Ratios. All right. And this is where I get to do a little tangent on exponentials are really, really powerful. They're huge because they explode really quickly, or they can unexplode very quickly, I guess, too, depending on what you're talking about. In terms of exponential growth, let's assume that you have like a bacteria, one bacteria that doubles every, I don't know, minute. So it doubles to 2, then 4, then 8, then 16, then 32. It's going to get bigger and bigger, and within like a few, like in 10 minutes, you're going to get up to, 512 bacteria. And then in the next 10 minutes, you're going to be in the millions of bacteria. They explode really, really quickly. They get really, really big, really, really fast.
Bacteria will there be in 24 hours?
In 24 hours, because you'd have to calculate minutes, so you could do that. It would be 2 to the power of, in parentheses, 24 hours times 60 minutes in an hour. It's so big that my calculator can't handle it. How many would I have in 1 hour? I would have 1 followed by 18 zeros, number of bacteria. These things get big very, very fast. And it really depends on what that base number is. I said it doubles every time, but what if it only increased by 1%? Then it wouldn't explode that fast, but it still gets faster than linear depending on what that linear equation is. And that's this whole unit, and I didn't talk about it, but our whole unit is comparing, well, it's not maybe comparing, but it's talking about exponential growth and decay, and especially how it relates to linear models. You'll see that I'm talking about just describing linear versus exponential. Even in our last lesson, 8-9, I'm still comparing linear versus exponential. I want to be able to compare and contrast those two. All right, so graphical differences. One of them is increasing at an increasing rate. One of them is just going up at a constant rate. Anyone want to take a guess which is which? Who has their card still? Esha?
The constant rate is the one that says straight line.
Straight line, is that going to be linear or exponential, this straight line?
Linear.
Linear, yeah. And you're correct. Not only is it linear, but it is a line, and that's where this word line comes from. It is linear. Thank you, Esha. And what about the other one? That must be
exponential.
Exponential. And I'll make a note here, and you should make it as well. This is only an exponential graph for growth. Eventually, I'll be showing you a very formal graph on what exponential graphs look like and what exponential growth versus decay looks like. Like if you have some radioactive isotope of, I don't know, gold or lead, I don't know, it would look a little bit different. You just kind of flip it over the y-axis. That's enough about those graphs. I'm only gonna touch on that briefly today. And then contextual differences. So if I see a real world problem and I see the words, it's going to double every minute, or double every hour, double every day, or triple every second, or maybe I'm increasing by a certain percent, because that percent will grow and grow and grow as well. These are words that indicate that you're going to be doing what? Is it going to be a linear or is it going to be exponential? Who wants to take a guess? And it's going to be someone that has a card. Yeah, Emma. It is indeed exponential. And that means, Emma, the last one has to be linear. Thank you. Yeah, linear. You're increasing by a constant amount. Like every 3 hours, this many snowflakes fell on the ground. Like that's a constant amount. It's just some number every single amount of time. All right, let's see some examples. Everyone is done writing. First one exponential, second one linear. All right, example number 1. I have a bunch of different tables for you. You need to decide if they are linear, exponential, and some of them might be neither. What would neither look like, Mr. Sandell? Well, let's see, right? You already know the first one, Wyatt?
No, I was going to say what neither might look
Oh, what might it look like?
Like with the x not having a constant rate.
That's definitely one thing that will give you neither. It could be a bunch of other things too. I saw Ash's hand next, and then Eamon's after
Could
her.
another neither be where it's like it's exponential and linear at the same time on the same line?
Yeah, it depends on what you mean by at the same time, but generally, yeah. Eamon?
Doesn't match up to either exponential or linear equations.
That's yeah, that is the definition exactly. Yeah. So if it like multiplies by 2 and then adds 5 and then multiplies by 3 and then subtracts 2, like that's not a constant pattern. It has to be the same pattern times 2 times 2 times 2 or plus 4 plus 4 plus 4. If I randomly said plus 5, no longer linear. It's not the same difference. Yeah, Kira.
So difference is if you're adding or subtracting, and ratio is if you're multiplying or dividing.
That is 100% correct. And maybe I should add a little symbol in here that says common difference mean add or subtract. Ratio means multiply or divide. And if I'm being really formal about it, I can say it's always multiplying, and really you're multiplying by a fraction when you're dividing. 1 over 3 is what you're multiplying by. So I'm going to kind of do a slash through the division symbol because it's really just multiplying. Exactly. Okay, so let's do example number 1. First, you always are going to check your x values, and if they are increasing by a constant amount, then you may ignore them. Anyone want to analyze the x and y values on the first table, Ugo?
7.
What, adding 7? Okay, adding 7, I get 5. Okay, 12. Okay, I agree with you. Yes, it looks like we're adding 7 each time. What about the y values? Oh, yeah. So times 3 to get 1, 3. Yep, times 3 to get to 9. And that is indeed times 3. And Ugo, what conclusion do you have? Is that exponential, linear, or neither? Exponential. Thank you. Everyone write Ugo's answer down. It is indeed exponential. And it's kind of confusing what that means, so I'm going to do an arrow that says that table right there is exponential. All right, I'm going to go to the table on the right next. So top right. Who wants to analyze that table for us? First the x's, then the y's. Yes, Ulysses.
So it's like adding 2 and 2.
Every single time? All right. And what about the y values? Adding 9, and yeah, adding 9. So each of them is adding 9. So what conclusion do you draw from that? Is it linear, exponential, or neither, Ulysses? Linear, yeah. Everyone write down his answer. It is indeed linear. Question, what?
What should you do if you're done with the notes?
You may begin on the homework. It should be up. All right, next table. Who wants to analyze the x's? Who wants to analyze the y's? Does everyone have their card in yet? I think so. Yeah, okay, Kira, go for it.
Okay. I'll do that. So 34.7 is plus 3. It goes up by 3.
Okay. Plus 3 and plus 3. So we can ignore it now. And then the y's.
Oh, should I do the right?
Oh, if you don't mind. I can choose on some. Or,
It goes plus 2, then it goes plus 4, then it goes plus 6.
okay. So what conclusion do you draw from that?
It's neither.
It is indeed neither. Thank you. Is it neither or neither? I don't know. Tomato, tomato type of thing, right?
Like potato.
And who wants to do our final table? Yes, Emma.
Okay, so you add 1 for the x's.
Adding 1, adding 1, adding 1. All right, so we can ignore them. Keep going.
For the y's, you multiply 2.
Times 2, times 2, and yeah, times 2. Very nice. So what conclusion do you draw from that?
Linear? Or no, exponential.
It is indeed exponential, yes.
Oh, I get it, like exponential.
Yeah, the variable is in the exponent. And then finally we have example 2, oh, not finally, we have example 2 and then 3. Example 2, I need someone to read and then a second volunteer to answer. Who wants to read first of all? Jade was first.
Every year, the number of people playing a certain video game increases by 3% every year. Is this a linear or exponential relationship?
All right, thank you. Nice reading. And someone else answer. Is it linear or is it exponential? Ulysses. Ooh, careful. So if it's a percent, if you ever see the word percent, it's going to be, yeah, exactly, exponential. And this is usually the point where yeah, go for it, Esha.
So whenever you see a percent, that means it's multiplication usually?
Yes, and the question is why. That's a perfect segue to what I wanted to talk about. So it is exponential. Anytime you see a percent, it's exponential, but why? Because when I increase by 3%, what you're actually saying is, well, I guess you're saying two things. First, you're saying simply, I have my 100%, which is what I didn't change anything, and I'm adding 3% to that. And you might be thinking, okay, well, that sounds like I'm adding the same amount each time. What you're actually saying is it can turn these into decimals, and I'm saying I'm really multiplying by 1.03. So there's going to be a giant part of this unit that I'm going to convert, or I'm going to teach you guys how to convert percentages into decimals so that you can multiply, because multiplication is what it means to be an exponential function. If I multiply by 1.03 over and over and over again, it will have exponential growth. So that's my very short and concise way that doesn't make sense maybe yet, but you're multiplying by a decimal, even if that decimal is still really, really close to 1. If I multiply by 1, it's not changing. 1 times anything is itself. And then example number 3, I need someone to read and answer at the same time. Who's got this one? Esha, go for it.
Okay. In Lee Binding, 34 cars pass through town every hour. Which graph best models this relationship?
And which one would you choose?
I would choose B because it's the same number every hour.
Every hour, and B is what type of function? Linear. Well done. That is the correct answer. And that concludes Notes A-1 question cure.
So, why is the exponential one curved?
Why is it curving? So we can make a table to explain why it's curving. So each time you're increasing by slightly more. So let's come over here and make a table.
Aren't you always just increasing by like multiplying by the same number every time?
You are. So I'll show you what it looks like in decimals really quickly. So let's go ahead and add a table here. My x value, let's go 1, 2, blah, 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 like that. Choose a number, I don't know, 1. And then do you want to multiply by 2 or 3, or what do you want to do?
2.
Okay, so next number is 4, 8. And then look at what's happening to our graph. I'm just graphing these points. 4, 8, 5, 16. And I need to scale my axes so that I can actually see what's going on. My y-axis, I want to come out to 10 and -1. My y-axis, I'm going to come up to 500. And let's keep going. So 16, 32, then 64, then 128,
256.
512. This is always going to have some sort of curve to it, and it's just a property of exponentials. When I double it, or even if I multiply by any fixed amount other than 1, it's going to have some sort of curve to it, either curving up or curving down. All right, I need to get a fist of 5 on how well we can do these types of problems. So all of these, example 1, 2, and 3, how well can you do those? 5, 5, 5, 5, 5, 4, 5, 5, and 4. All right, thank you.